For example, why we need to use classical computers? So for example, I can say 2 cube 8, 2 power 4, 16, fine. So how much time it will take to respond, or how much time it will take to complete a particular problem statement, or how much time it will take to get a solution. For example, when I ask you the question 2 power 128, it may take 2 minutes of time. Maybe 2 power 1024. It may take some more time. But classical machines are computationally fast, so that we convert our decimal number system into binary number system. Because you need fast computation, that's why we use classical computers. On classical computers, we perform our computations very fast with our intelligence. So in between these spoon feeding, we come up with a automation or machine learning algorithms to automate the process. So present up to this point, I talked about decimal number system and binary number system, right? Now a new programming paradigm will come into the picture. That is a new computation system called what we call quantum computing. So manual mathematical approach, manually, or classical computing and quantum computing. So this journey is evoluting from base words to where we are not able to solve our problems within a polynomial time or reasonable time. That's why we need to start working. We need to identify, we need to discover something. On top of that, we pass all the values to that run because it is completing the work within a minute of time, within a second of time. That's why people are using classical computers. On top of the classical computers, people are executing all these machine learning algorithms, cyber security, whatnot. All applications, fine. Now, what is the problem with classical computers? Why people are talking about quantum computing? Any specific reasons? We mentioned one reason that computation is high with the classical computer. That's why we start our working on regular machines. Now, in case of quantum computing, because of the what we call the best principles supported by the quantum, those values or those particular principles play a vital role, and whatever the problems solving by a classical computer within exponential time, the same problem, not all the problems, some of the problems are successfully executed by quantum machines or quantum simulators within polynomial time. That means two persons are there. One person solving a problem, he'll take 1 hour of time. Second person, he tried to solve it within 10 minutes of time. So which one we prefer? 1 hour or 10 minutes? Of course, we go for what? 10 minutes, right? So in the same, there we come into the picture of the quantum computing because of those entanglement property, because of that superposition property principle. Quantum computers are executing the computational capacity or the time taking to solve a problem for quantum computing are far more better than the classical machines or classical machine learning algorithms with respect to some of the portions, some of the algorithms, not all the applications, some of the time. So in this session, we will talk about in what way, for example, in previous session, maybe you know about what is qubit, the basic unit representation of the metric in quantum computing calculations and measurements. That is called a qubit. It representing a quantum state. That state may be in all the ways. So now the quantum hardware is still that it is evolving. We are working some of the machine learning algorithms or some of the applications on top of the classical computers. You know that classical computer supports binary numbers only. For example, many things are there. But for a base instant, binary number system, either 0 or 1, either true or false. But quantum computing support a particular qubit at state which is undefined or uncertain until you measure it. So how that particular qubit is possible to handle by a classical computer? Not possible. So our base language is, before classical computers, we are converting decimal number system to binary number system. Now we have a requisition or we have a need that converting that binary number system, 0s 1 or 0s and 1s are bits into qubits. Because if you are designing something on by using quantum algorithm doesn't understand what is 0, what is 1. Classical computer doesn't understand what is 8 and 9. Classical computers doesn't understand decimal number system. That's why they're converting everything into binary. In the same thing, quantum machines or quantum simulators doesn't understand what is 0 and what is 1. So what we need to do? What is the necessary point here? Put someone post in chat box. Quantum simulators or quantum machines doesn't understand zeros and ones. So what we need to do? I said there 2 points. One is qubit, second one is bit, classical bit. So quantum machines or simulators doesn't understand zeros and ones. So what we need to do, in what way you are transmitting, you are transforming, or you are encoding decimal number system to binary. In the same way, converting these bits into classical bits into qubits. So how to convert these classical bits into qubits? First point. Excellent. Thank you, Professor Nagar. Yeah, right. Integrate classical with quantum. So in that case, your base hardware is not quantum. Your hardware supports binary number system only. On top of that, we use some quantum simulators. For example, in our demonstration, in our session, we talked about Qiskit and vanilla. So in middle of this one, we need a conversion from binary number system to our classical bits into quantum bits. That is called encoding. So forget about the advanced machine learning algorithms, forget about all these classification, regression. Before that, what is the point? What is necessary? To convert the base level, convert a classical bit into a particular quantum state. That is called encoding techniques. First, we will talk about encoding techniques. Once encoding is completed, we are existing with the platform. On that encoding platform, where we need to where we need to put our qubits in different things. For those things, we use kernels and some other things, vectors. Afterwards, once conversion is completed, then according to application, we use those things. So today, the entire session is about, at end of the session, I try to compare one classical classification algorithm, one classical machine learning algorithm with one quantum machine learning algorithm, and we will see in what way the two are executed and which one is best. I said that for not all the applications it is good. So whatever the applications are good, we talk about those things only, right? My screen is visible to you all. Is it visible?
Yes, sir. Yes, sir.
Yeah. Thank you. So today our topic is about quantum machine learning for next generation AI. So here I combine the mathematical approach, theoretical explanation, and according to time convenience, I try to come up with some sample snippets. In what way we can represent. Maybe in previous sessions they talk about what is poly X, poly Y, poly Z gate, and rotation X, rotation Y, rotation Z gate. In what way they're changing the probabilities, in what way they're changing the phases. So now we convert the theoretical aspects into on Qiskit platform. How can we represent a poly X gate? How can we represent a poly Y gate or poly Z gate? From that poly X, Y, Z, for amplitude purpose, for probability purpose, how we are adding rotations. So when rotation changes automatically, in what way it is converting that classical bits into quantum qubits. Once qubits are changed, how can we define this state? In that state, how can we represent an entanglement? How can we represent a superposition? By using those coherence, inference, superposition, entanglement, how can we address the real-time problems? That is the thing here. For example, if I'm talking about a superposition, so you know that. Okay, I'll change this next. So it is one of my best favorite code. If quantum computing has not rocket, you have not understood it. So why I'm telling this point is, for example, I can mention two fingers here, two fingers. So from left to right, I just mentioned this point. My point is, I want to walk from one end to other end like this way. A small finger, big finger, or small, shorter finger, taller finger. So this is the situation. So I can show like this. So here, just this is left leg, this is right leg. So simple thing is you want to walk from here to here. It's in motion, right? Again, left leg, right leg, left leg, right leg, left leg, right left, right left, right left, right left, right left. So my question is, I selected 2 persons in our team, 2 individual persons. So for first person, for first faculty member, I ask you about count or just capture. This is a motion. So please take a screenshot or please take a photo. I need the photos or screenshots of a picture which the left leg is forward. Left leg should come first. Capture those photos only. For second person, I said that the right leg should come first. So in this motion, which person wins? Whether those 2 persons get the same satisfied with the answer. For example, a motion question is, we are moving from this side to this side with 2 legs, left leg and right leg. A person is walking like this way. So while motion, what I'm asking is, take a screenshot or take a photo. So while taking the photo, I ask one person, just measure about or count or collect the pictures or screenshots. In that screenshot, left leg should be come forward. I need the screenshots of left leg one. Left leg should be front. Left leg should be front. For second person, I said that right leg should be front. At end of the motion, whether which condition is true, whether these 2 persons are get the answer or not. You can post in chat box. Whether these 2 persons are getting their answer, whether they are successfully able to capture the assigned task or not.
Yes, they will be able to.
Yeah. So
because only the direction is towards the direction and the destiny is important.
Right.
So, goal state.
Yeah, but here in classical computers, usually for some of the applications, not for all the applications, sometimes we said that if it is 0, it should not be 1. And if it is 1, it should not be 0. But in this context, when a person is moving from one place to other place, the metric calculated by one person is not equal to the metric calculated by other person. So while this motion, this first person is able to capture the frame because he is measuring something. The second person is also catching the same thing. So for 2 things, 2 conditions are satisfied with that interval of time. So can I say that within that particular bound, these 2 are acting simultaneously? That is called superposition. It is not 0, it is not 1. Right? So for the point only here, one best example, that Schrodinger's cat equation. So here, this was the theory was developed by Schrodinger. He said that, for example, there is a cat. So one box is there. That box contains a poison, a leakage gas, a poisonous gas is leaking, and a cat is inside that box. So this particular person released the gas, and inside the cat, cat is able to take up the gas, everything. After some time, 20 seconds of time or 30 seconds of time, my metric is, my certainty is, my question is whether cat will die or whether cat will survive. Any right answer? Simple thing. 2 things. One box, and box is covered. We are not able to see anything inside the box. Inside the box, 2 items are there. One cat and one poisonous gas. This poisonous gas is releasing, and the cat inside that box. So after some time, whether the cat will die or not. Until you didn't measure it, until you open the box, you cannot decide with the 100% probability the cat will die. You cannot decide the 100% probability the cat will alive. That means this is called wave particle duality. So if you are not measuring something, it is an emotion. Then I ask you about, for example, I ask you one question: what is the time now? What is the time now? Some people say that maybe 2:22. When you reply with my answer, by that time it is 2:23 or 2:20 with 45 seconds. That means when the time is babe, when I ask you some question, when I ask you to measure something, at that particular instant of time, you bring up something, you assume that it is the final answer. But for your question, answer will change again. Answer will change again. Answer will change again. That property is called superposition. That representation is possible in quantum machines, but not with the classical machines. That's the beauty of quantum. By using these basic implementations only, we do some magics. I'll explain how can we do all the magics and everything by using. There is no magic until you are not able to understand this as it is magic only. But once you understand the basics and the basic math, you can do everything. And next point here. So I don't want to mention all the basic definitions and everything. Just it is in what way a normal computer different from quantum computer. So with respect to searching process, I come up with one sample video. What's that? This one. Are you able to see this one? Are you able to see this video? So here,
Yes,
the
sir.
purpose of this video is in what way the normal search is different from quantum search. In what way the classical computer performs the searching algorithm. In what way quantum search the process for a solution, for a path. This is a game. Usually in our childhood days in newspaper, we got this one. That is one entrance is here, and you want to identify the exit from the other side. Simple game. So for this one, for example, if you go this way, maybe stuck here, some wall is here. Again, if you go, you backtrack and again go this side, some wall is there. So in normal case of search, in what way we are searching, we are identifying the path to pass from one end, and we need to leave from the other end. This green symbol is open gate here. This blue symbol is starting point. Let's see in what way the searching process will be implemented by normal search and quantum search. So if you look into that, at a time, multi-searching is possible because as I explained the superposition, it can calculate, it is able to capture all the possibilities at a time because it is not searching for, it is not going for zero direction, it is not going for one direction. Because of this superposition principle, it searches everything at a time. See here. If we are increasing multiple qubits automatically, we can increase the searching process, we can improve the searching process exponentially. This is one simple instant. Before we are going to the advanced algorithms, you need to understand in what way the quantum principles help by performing a basic operation, searching operation. So if you look at the normal search, it is sequential. Some people maybe assume that here some concurrency is there, parallelism is there, code to dual to code, many things are there. But some of the applications, even though first work is completed, second work is very fast, this work need to wait for the first work. There should be a dependency condition. Because the second person doesn't understand what is the outcome of first, but quantum can, right? So this is about something related to that superposition concept. And next, entanglement. So, just a minute. Able to see my screen? Okay, right. these are some of the points, some important points, some entanglement. So the entanglement means the state of one qubit can depend on other. So in what way it is related? The state of one qubit can depend upon. For example, even though this distance is more, if one bit changes, automatically, if it is an entanglement property, the other also change the same thing. If it is 0, it also by default becomes 0. If it is 1, it also becomes 1. So, but what is the advantage of this particular change of entanglement? I can go with one sample example here. So, this is something about a quantum key distribution. In what way two persons are able to share their key without depend upon the third party persons. That is simple thing. So entanglement means if we are distributing key to multiple ways, those two particles, two qubits in a sync state. If it changes automatically, it also changes. That means, like, for example, establishing a connection or tinkering a rod in between two plates. Based on the rod, if it falls left, it is also left. If it is right, it is also right. So in this case, so here two persons are there. They want to share their key with each other from this quantum key generator. So if you look at this point, entanglement means depend upon this direction, it is directly entangled in this direction. Both are in the same direction. These two are in entangled state. If it changes, it also changes. If this direction changes, it also changes. These are multiple qubits. At receiver side, we have a different positions, that is row wise, vertical wise, or left orthogonal, right orthogonal. These are continuously rotating, that is called randomization process. When these are rotating multiple times, when multiple qubits are coming near to the polarizer, state of polarizer, this particular polarizer are at that time, if it is in left orthogonal, at that time multiple qubits are coming. Among those multiple qubits, which qubits are exactly left orthogonal, those only filter outside. Rest of things are discarded here. In the same way, if it is horizontal, if it is vertical, we filter those things only. If you observe these polarizers here, they are rotating here. First rotation, again rotate, again rotate, again rotate, again rotate. So like this way, while receiving, we capture everything. So based on the rotations and the matched patterns are coming outside. Even though the third party person may be sent 1028 qubits, but the polarizers supported by the intended Ellis and Bob, those two are in entangled state. Entangled means those two qubits are in a relation. So one changes automatically, other also changes. So there is no point of sharing by the third party persons. These two people are in entangled state. And once we receive that one, so when we're sending multiple qubits, we assume that we receive all the qubits. But in this case, whatever the matched patterns, they filter the key, whatever the matched patterns with the direction of the qubit, with the direction of the polarizer, those only filtered. If all these red marks means they're not matching. See here. If you look at this one, see, this is left and right orthogonal, and this is horizontal vertical, but the directions are different. So these things are discarded. If you look at this one, left orthogonal, same direction, left orthogonal direction. So these two are in the same state. So whatever the matched patterns, we filter the key that way. That key may be used as an ODP or encryption or decryption for different purposes. So these two are final key, matched keys. This is called, in this way we can do encryption in a secure way. On top of this one, many algorithms are there, but for explaining entanglement, I am showing this example. But our discussion is different, quantum machine learning. After this one, we go to those things. But in this case, for example, if eavesdropper or if third party hacker is there, for example, he tried to capture something. So when he tried to capture something, See here, when he captured, in first case he is not captured, he is not disturbed that one. So these two directions are same. That means these two are entangled. But when the second, third, that particular third party person, he disturbed that one, he take up one bit and replace with other bit, automatically they lost the quantum entanglement principle. Like this way, they easily captured. There is a same base map formula is there, but this one we use some Hadamard gates in superposition entanglement, and I will show those gates also. So in this one, there is no alignment, there is no relation. So when these two particles are not in entangled state, those two are automatically captured by the at the polarized state. Let's see in what way this happened. See again, see here, it is left orthogonal, it is upwards. There is no entanglement. And again change. So when this way, when we receive the thing automatically at the polarized state, we calculate what are the misspelled, what are not in the entangled state. When we just check the directions of the both things, if both are same direction, we capture it and consider it as a not compromised bit. So at this way, in second case, if third parties existed, if any unintentionally someone tried to capture our data, so based on the relations, see here, they are not related, not matched bits, not related. We discard all the things, and here sometimes the quantum bits may be changed because of that noise issues. Still, we don't have any sophisticated hardware. Because of the noise, also some bits are changed. For that purpose, we come up with a threshold calculation value. In the threshold calculation value, if the value is more than threshold, assumption is it is not automatically garbled because of the noise. Someone is tapped that one. Someone is changed that one. So for this purpose, we have some specific algorithm is there. Quantum error correction algorithm. So there they calculate that particular, they implement the algorithm and they calculate the error rate. If that error rate within the threshold, then go for that one, process the QTU securely. If not, generate a new key. So this is something about, this is one of the best application of entanglement. Hope you understand this one. So as of now, we talk about the basic information. I'm not discussing any coding part. Now, yeah, this is completed. This is in what way these two things are different. Anyways, you already familiar with this one. So here I mentioned some timeline of quantum computing from 1935 to 2017. As part of my, we are working on some survey paper on quantum algorithms. So we got in what way, what are the different types of Bell inequality, EPR paradox. For example, in case of Bell inequality, Bell's inequality in 1964, he proves that quantum behavior is fundamentally different from the classical physics. In what way we talk about all the principles by that time only. So this is something, a timeline from 1935 to 2017. So simple, yes, detailed meaning is quantum computing evolved from the strange theory to real machines available worldwide. That means the starting stage, they pass statements, but there is no proof. But nowadays, we are seeing that entangled properties working. We are seeing the superposition is working. We are successfully implementing all these quantum gates on some platforms, and we are waiting for the full-fledged quantum hardware also soon. And next one. So, for example, this is something like how many companies spend, because why we need to work upon quantum, why we need to educate about quantum means as a faculty members. For example, in many colleges supporting campus placements, now they are asking about AI engineer or cybersecurity analyst or full stack developer. But when era goes for after 5 years or 10 years, there might be a chance of getting that entire in what way artificial intelligence come to the basic part of compulsory course. Quantum also come into the compulsory course. There might be a chance of getting more. Based on this figure, you can understand that how quantum computing hardware has rapidly advanced from past 20 years. So For example, if you look into that research groups like IBM, Oxford, Berkeley, Stanford, they start with a basic 2 qubit. They start working with 2 qubits. By 2019, they get supporting 128 qubits also. So when number of qubits are increased automatically, we can increase the computational power also. So when the multiple problems are solving within a reasonable time, then everybody want that particular mission only. Even though it is priced more, people are trying to work on that one, trying to use the same product. So when the product sales increases automatically, we need technical support. For technical support, we need manpower. So based on that, we can assume that in future, it may lead a wonderful platform for learners. Next. And this is something about how many dollars they spend from 2022 and approximately by 2030. So this particular shows that how rapidly the global quantum computing market is expected to grow in between 2020 to 2030. So basically in 2020, if you look at that one, started the $260 million of reflecting that early stage research and limited commercial use. But just imagine by 2030, it goes up to 9.6 billions. That much amount, multinational companies spending that much amount on that one for development of hardware, procurement of all those things. And this is something about, say, quantum. It is from a different source. Like from the market research, we extracted this one. On top of that, we perform some metrics also. So this is something about future of quantum computing, in what way it is useful. Now coming to the point, in what way it is related to our topic. For example, I can say that quantum computers can useful for artificial intelligence applications. For instance, quantum computing can help improve the accuracy by multiple machine algorithms. For example, recently people are writing many papers to identify the COVID disease, to identify the image processing. Many things are there, breast cancer detection, leak detection. They come up with 98%. But when that is the label data, structured data, unstructured data, for example, if you want to work on 20 GB data for searching process, 20 GB. So classical computer doesn't support superposition. Classical computers doesn't support classical machine, classical algorithms, doesn't support entanglement property. In that case, it may take some 200 hours of time. Even though if you're working on our small systems for a research work, almost we need to spend 20 hours of time. Every night we execute algorithm, we go home and we come back again. At that time, we don't know, we are not sure whether it is complete or not. For a small 2 GB data, for generation of multiple images, maybe all the faculty members already, you also face the same situation. But in case of quantum, that improves the accuracy within limited time, with the help of this feedback of AI, and learn from mistakes very fast. And second application, that may be national security, of course. It can be used for spying and military operation simulations, and design can replicate components, almost something. Cryptography, just now we have seen that the quantum key distribution, material science, finance, healthcare, many possibilities are there. Again, it is a combination of artificial intelligence with quantum, cyber security with the quantum, many combinations are there. I can say that point. Now come to our real work. As of now, we talk about the basics and in what way it can support. You need to understand what is the reason to talk about quantum, in what way I can relate that quantum computing with the classical machine learning with the class, and why we need to move to the quantum machine learning. So, you know that machine learning is computational. You already familiar with all the things, what is the fundamentals of machine learning, and what is supervisor, what is unsupervised learning. For example, if it is a label data, the model is start using input-output based. The main intention of the supervisory is to predict the correct label for new unseen data. I can say that, for example, email spam detection or disease prediction. We already implemented many algorithms. So specifically, we talk about, we will go with the classification algorithms, support vector machines, or classification decision trees, logistic regression. Many combinations are there. If it is a regression time, that is a linear random. Again, it contains many parts are there. In case of unsupervised, it is something like unmetric or unlabeled data. There is no predefined outputs. We need assumption is there. So the main purpose is discover the structure and where it belongs to a particular modular cluster or relationship. So in this case, we can divide the customer segmentation or dividing, grouping a new articles or anomaly detection or fraud detection. For this one, we have a K-neighbor algorithms, K-means hierarchical clustering, and dimensional reduction. Some algorithms are there. I'm not aware of all the things now. And next, reinforcement learning. It is something about. I can say that it is not exactly whether it is concrete, it is existing or not. Something like trial and error, using some rewards and penalties. The main purpose is find the best action in that particular situation to maximize long-term reward. So the best thing is we go with the autonomous vehicles, robotics, or gamification by using AI, by using Q learning and deep neural networks. Again, it contains semi-supervisor and self-supervisor. We call it as a deep learning, and many models are there. Right? So, next one. So now come to our quantum machine learning. What is this? Why we can talk about quantum machine learning? So specifically, quantum machine learning is a field of the computer science only. It is intersection of quantum computing with respect to machine learning properties. As of now, we talk about supervised and unsupervised things. So it leverages quantum computing principles to enhance or to improve or transform how machine learning tasks are approached with the potential to achieve significant speedups. The point is, you need to understand it, speedups, and improve the efficiency for certain problems. There are many problems are there. I'll explain what are the problems, specific problems, where quantum machine learning is somewhat better hand than classical computers. And next, we already talked about this one, fundamentals of what are the pros and exponential speed and potential, right? Concept of the quantum machine learning. So core concepts is something like quantum computing basics. So it is something like principles of quantum mechanics. We talk about such as superposition entanglement to process information in multiple ways, which is not possible with the classical computers. And the quantum speedup, we already talked about. So here, quantum speedup sense is quantum algorithms what can I say that can potentially solve specific computational problem more efficiently than the classical algorithms. So I can say that maybe you done with Shor's algorithm, right? Shor's algorithm in previous sessions, Grover's algorithm, Shor's algorithm. Specifically in Shor's algorithm, it can factor large integers exponentially faster than the best known classical algorithms. So Grover's algorithm can search any unsorted database quadratically faster as compared to classical algorithms, right? So here we talk about what is quantum data, what is quantum speedup, and what is quantum assisted enhanced AI models. Many combinations are there. So here I'm showing in what way the quantum machine learning differ with the classical machine learning. So in case of quantum algorithm, we use quantum principal component analysis. That means its main object is to perform dimensionality reduction more efficiently by exploiting quantum superposition to process data in specific a part of the operations. If you talk about support vector mission, in case of quantum support vector mission, to improve the classification task by using that quantum computing to fast kernel evaluations. So here in coming slides, we talk about that what are the quantum kernels and what are the data encoding techniques, in what way those encoding techniques are related to these quantum kernels, and by using these encoding techniques and quantum kernels, how can we build a quantum classification algorithms which will show a better accuracy than the previous existing algorithms. That is something about the point here. So specific difference. When to use machine algorithms, when to use QML algorithms. It is something point is It is not possible to discuss all the things, but it is spend a minute of time on this one.
పోయావా ఏం వెళ్ళలేదు మరి హెల్త్ ఇష్యూస్ పెట్టావు కదా
Sorry.
నీకు ఫ్రెండ్స్ ఎవరు లేరా
So, as I explained to when the data sets are very big, very complex, at that time the better suitability is quantum machine learning for high dimensional features. For problems that are well understood, data is genuinely quantum for quantum engineering, and small training data sets available in case of research exploration, or in case of deep searching process. It's in case of unstructured database searching, in case of large integer factorizations. For those specific applications, quantum machine learning is well suitable as of now, but still counting. People are working on many other applications also. Next, now come to the actual part, because I explained that we talk about what is the purpose of encoding, why we need to convert that mapping classical data to quantum states, because in case of data encoding, it is a procedure, a process for transforming or encoding classical information. I mean to say that bits and bytes into quantum states. So the primary encoding techniques are many combinations are there. It is basic encoding, amplitude encoding, angle rotation, hybrid encoding. Many things are there. Many things. So now we will talk about for this one to implement. I try to explain what is basic encoding. Once it is explained in what way, what are the basic gates we need to implement this basic encoding, and in what way we can convert it. Let's see those examples also. So I believe that you are already familiar with these poly X, poly Y, poly Z gate. You can post in chat box whether those topics complete or not. I hope they completed. As far as I know that. Is it or not? Poly X, poly Y, poly Z? No? Okay. Right, okay. So here the point is a single Hilbert space represented as that H2 value. That value is, it is in between any combination of zeros and ones. It is a standard basis vector. That means you know that it is a quantum state 0. It is a quantum state 0 by default. It is representing with a column vector 1 0. It is ket 1 or quantum state 1 by default, so it with a 0 1. Right? So, but what is the purpose of that one? In what way they are useful? For example, so all these things are we can represent as a log space for a quantum bit. Usually, our journey starts from vectors and vector spaces, but here I'm not talking about vector spaces, because to represent a quantum state, we start with the vectors only. For example, for ket 0, and ket 1, this is the way. If you pass this classical bit, these encoding techniques is able to transmitting into a qubit. For this transmission, for conversion of your regular vectors or state vectors or your Python list in general, to transmit those things from a regular classical vector form to a qubit state. For this purpose, I need what? Encoding.
అవును అది
Encoding techniques. It contains many things are there. For example, if you look at a block sphere,
ఎవరికి
because I need to talk about why complex numbers, why in what way we can represent this quantum space. For example,
సరే 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 సరే
if you assume it is a block sphere
సరే సరే
and I considered a 3D model. Maybe it is x-axis and it is y-axis. Y-axis and it is z. In this state, I consider two angles.
మా ఫోన్ చేస్తాను
Hope you know about Pythagoras theorem and everything.
జాయిన్ అయ్యారా
If you represent this one, and
కాల్ చేశారు ఆల్రెడీ
we call it as this is theta, and
నాకు మెసేజ్ చేశాను నెంబర్
it is phi, and it is theta.
సరే సరే
This particular is called, maybe it is a quantum state. If it is there,
చేశారు
in this region, theta starts from 0 and phi also 0. So this z is representing as directly at 0. That means what? 1 0. So exactly opposite. If you draw the line, come down side, it is changing the spin probability. Then this value is called pi. You know basic trigonometry. 0 to this entire is 2 pi. This 60 degrees. It is pi value, but the sign is 0. That is called. We just change the sign z, negative z, and exactly opposite means it is a ket 1. That means 1 0. Because you want to representing multiple classifications for multiple angles, multiple probabilities. In quantum sense, we call it as a aperture. In the same way, if it is 0, if it is pi, what is this? What is this value? Pi by 2, yes or right? In between 0 to 180, pi by 2. And here the value is also pi by 2. This is represented as same on y-axis. This is called rotation. To rotate from here to here, we use R by gate, rotation y. Anyways, I'll show that one in this way. Anti-clockwise. In this one, this particular positive plane or hyperplane, we call it as a, there is half probability of getting ket 0, and again half probability of getting 1. It's exactly opposite. What is this one? Here, the value is pi by 2 only, but the space is minus pi by 2. Exactly, negative value. Here, it is, we can represent as a y-axis. These two are z-axis. These two are y-axis. These two are x-axis. Like this way, we can fix the point for all the rotation of the qubits. There are multiple possibilities are there, but we can fix up x-axis, y-axis, z-axis. But those things, I can start my journey with the vector. That vector should be converted into a quantum state. Multiple quantum states combined will form a gates. From multiple gates, we form a quantum circuits. This is the thing. Once we calculate on an average, the quantum state for a particular angle, this particular angle, I talked about this angle, that should be equal to, and trigonometry, we know about 1 by root 2. For getting 1 by root 2, what is the value? What theta? This is the position. And for this one, sine theta by 2. And e power I, that angle, that phase angle, to change it. Because every time this phase angle is complex only. There is not a point of getting the numbers. When we are rotating a thing, it is maybe 45.6, 67.40. Angles always changes. By default, we consider it as the complex values. So here, this value is, every time we can replace with, for example, if we are here in this position, this value is e power 0, I into 0. When we are rotating here, this time, pi becomes pi by 2. So to change sign, plus to minus, minus to plus, like this way. So this is a basic representation of a block sphere. What is the purpose of block sphere? Can anybody guess? Here, that particular theta is a polar angle. That angle should be in between 0 to pi. And that controls the relative amplitudes are probabilities of either quantum state 0 or quantum state 1. That is measured from the north pole towards south pole. And phi value, that is for representation of angle. That angle may be at any point, that is 0 to 360 degrees, 0 to 2 pi. It encodes the relative phases between. So here 2 points to represent a probability or an amplitude, we use the angle theta. To represent a phase or angle, we use that phi. So in future discussions, we talk about these two angles frequently. So this is the base to implement encoding techniques. This is the base. Hope you understand that. For those who are starting quantum computing now, they may get some little bit of confusion, but it would take some time to understand what are things here. So that is what I mentioned the point here. So here normalization condition means you always you need to follow this particular condition. When we square the amplitudes, the probability should be 1. The complete probability should be 1. That 1 may be 0 because while measuring, there is no point of middle of the state, whether it is true or false only. While traveling, while communication only, the states are different. But while when measuring something, it comes with a certain probability. That is called normalization condition. So here I talked about complex numbers, the purpose of complex numbers. Next one. Now we back to our normal discussion. So as of now, I explained what is the purpose of vector spaces, and in what way vectors are useful to converting your things into what can I say that a quantum state. So in that case, for example, this time I try to compute these are these direct values, poly X gate, poly Y gate, and poly Z gate, right? So what is the purpose of X, Y, and Z? You know that one. Some two are used for, one is used for changing the amplitudes, and another is used for changing the sign, and some are both change in sign also. Right. So right. So in 3D space, it is the complex value represented as this value. For a single qubit, these are the values. It is entirely the purpose is to calculate what is exact matrix value for what is the vector space. Once we get the vector value, we are automatically converting based on that vector value. We can decide what is the angle, and followed by what is that amplitude value also. Right? These are the values here. So for even powers, we calculating odd powers. It is a long theory, but for representation purpose, and you do not need to remember all the things. In Python, we are good enough. We have a predefined libraries are there. For those who are starting their work in the quantum computing as a research, for those people it is necessary. But for application point of view, it may not be. You may not need to understand the entire depth part. You don't need. Right. For example, in what way we can calculate that theta value? I already explained. This is for what? Phase value. So in previous case, we talk about Rx theta value. So it is something like the exponential value of theta by 2 for X gate, poly X gate. X gate is by default 0, 1, 1, 0. It is a predefined fundamental value. So according to this Taylor series, you know that finally in previous time we calculated, this is a skew symmetric matrix. You calculated as a from 0 to infinity possibilities are there, but on simulated it is not possible to mention all the infinity possibilities. We consider some of them only, some of the left orthogonal, right orthogonal, horizontal, vertical, based on the angle what we selected. And these many, this is the direct formula. So for example, you need to set that A value should be the negative phasor of this one. That means indirectly the rotation gate of Rx theta is equal to, instead of, in the place of A, you just substitute this value. We are calculating for one phase only. So here, n equal to 0, up to infinity possibilities are there, 1 by n factorial, this one. In case of A, I replace with what? I theta by 2x whole power n. So here use the, the properties when we multiply x square multiple times. I mean to say that 0, 1, 1, 0 and 0, 1, 1, 0. So what is the answer? 0 into 0 plus 1 into 1. 0 into 1 is 1 into 0. 1 into 0 plus 0 into 1. And 1 into 1 plus 0 into 0. So by default is what? 1, 0, 0, 1. So if you are multiplying x square or x power 4 for all the even combinations, the value should be equal to what? Identity matrix. I value. Hope you understand that. That means I can say that x power 0 by default one value, and x power 1 it is direct x only one matrix. For x square it is identity. For x cube it is same x value. Like that way, if you're repeating x power 2k, identity value, x power 2k plus 1, that is what? X value. If you repeat the same thing, here I come up with the two classifications. One is all odd combinations. Second one is all even combinations. So in that case, if you repeat the same thing multiple times, first we consider that add even plus odd. We are combining both the things. This is equal to the final your theta value. That means after multiple combinations, finally we come up with a standard notation called cos theta by 2. Identity value minus I sin value. It's the same thing, sin theta 2 into the poly h by 2. So now substitute the matrix I and x. That means what? You know that I is what? 1, 0, 0, 1. And poly x is by default reverse 0, 1, 1, 0. So finally the Rx theta is equal to cos theta by 2. In place of I go with 1, 0, 0, 1 and minus sin theta by 2. In case of x, I go with 0, 1, 1, 0. So after multiple entries, finally you calculate that value is cos theta by 2 minus I sin theta by 2 minus I sin theta by 2 and cos theta by 2. This is the gate representation finally. This is entire derivation, but in Qiskit or Pennyline, you can just call Rx, that's all. You do not need to bother about all these complex implementation, but I want to give some basic idea in what way poly X or phase gates or rotation gates are combinedly useful in what way from vectors to this converting, and from here in what way we are performing the encoding techniques. These are the base math for encoding techniques, data encoding techniques, either basis or angle or amplitude or hybrid, many combinations are there. So this is something about Rx representation. In the same way, we go with what is that? For Y and Z also, based on the same calculation, base expansion, we go with these are the formulas. Just remember these things. Rotation gate for X, rotation gate for Y, rotation gate for Z. So as of now, any doubts? Okay, right? Now come to basic encoding. So here basic encoding, it is a classical bit string directly one-to-one change. One-to-one change means a classical bit directly converted into quantum state. For example, if you're representing 101, 101, I want to convert into quantum state 101. That means 101. That means what? Ket 1, product of ket 0, product of ket 1. That means 01 into 10 into 0. You calculate something. This is the final representation of the quantum state, right? But here we are not using any quantum magnitudes or probabilities or anything. So it is very simple, just converting classical bits into quantum state bits. So for example, by default, when we start a quantum state, it's starting with a 0, 0, 0 by default. So when your classical bit contains 0, no ordinary change. You do not implement anything. For example, if your bit is 1, you need to change it. So X gate is act as a NOT gate. NOT gate. That means for X, for example, I can say that by default, ket 0 is what? Maybe. It is 1, 0, maybe. So X gate means what? 0, 1, 1, 0. I go with 1, 0. So after multiplication, 0 into 1 plus 1 into 0, 1 into 1 plus 0 into 0. It becomes what? 0, 1. The 0 is nothing but what? Ket 1. So when I just apply a ket 0 to poly X gate, your final answer is poly 1. In the same way, if you are applying ket 1, 0, 1 to poly X gate, you will get what? 1, 0. That is called ket 0. So finally, I can say that X is at a NOT gate. So when you start your circuit, by default, when it is 0, do not change anything. When we are getting 1, you can change anything. So you know that your state vector in Python library, your index starts from 0, 1, 2 sometime. So with respect to these matching patterns, we need to calculate it. And so the main purpose is very simple. Here we are not using any low normalization. Use 1 qubit per classic bit. If classic bit is 1, we can convert it into, we are not combining entire list into a single quantum state here, but directly one-to-one mapping. That is the main purpose here. So here I mathematically I show the things also. It is LSB, least significant bit. It is MSB. So for this one, here B0, it is direct quantum state B0. For Bn minus 2, Bn minus 2, Bn minus 1, Bn minus 2. So here the number of qubits is equal to number of classical bits, just changing the phases. So now we go with some, in what way, as of now we talk about some mathematical proofs and everything. Now the point is in what way we can implement this basic encoding technique in the Qiskit. So for Qiskit, you need to install, you can go with the Jupyter Notebook or something else. First we go to this one. So here, if you can go to this place, or else for downloading this download Jupyter Notebook. So directly you go this one, you can install like this way. Conda install Anaconda. So once the download is completed, you'll get this one. One is Anaconda PowerShell prompt. Right. So here So if better, you can create one private environment. There you can look into first we need to install Quiskit. Pip install Quiskit. Of course, from my side, I already installed everything. And some people may be interested to work with in Penguin also. You may go with that also. Penguin is good for quantum machine algorithms. And the next Pip. Right. These three are mandatory. So once we install that one, automatically click on Jupyter Notebook. It opens, right? So for that one, it is a basic representation. Before you starting any installation, you go with all these installation for representation class and everything. Install NumPy and Scikit and Quiskit circuit, Quiskit quantum. These are the basic things. So I post all the things in chat box. So before you start, if you are trying to explore something on Quiskit, on specifically on machine learning algorithms, so go with these particular packages. Once you got here, next. Now you want to represent, you want to implement a particular data encoding technique. For Quiskit, you need to import. Here, one default method is called quantum circuit. Inside the quantum circuit, it's supporting all the gates also, quantum circuit. So as I explained, in case of basis encoding, you need to read one vector. You can take classical data by using a variable or an object bits equal to. I can go with 1, 0, 0, 1. Right. Now read one more variable QC. Here I want to calculate by using quantum circuit. So here I am passing bit values, 3 values I pass it, so I need 3 qubits. I need 3 things. Now I need to run my show from I to number of bits. So bit contains how many things are there? Bit n. There is one function called I don't enumerate is there or not. It's supporting the number bits. And if bit is 0, by default your journey starts from 0. You don't want any changes. For example, if bit value is equal to 1, then you need to apply what gate? Can you guess? We explain something. If bit equal to 1, we need to change that state. For that one, from quantum circuit, I need to apply X gate. That I start from your value, index value, I. Now you want to print the entire qubits. I want to draw it. That is the. Spelling mistake. Quantum circuit. Right. See here. So here I'm passing 1, 0, 1. According to the data encoding scheme, if it is 0, I'm not applying any gate here. If it is 0. The second value is the second event 0. For bit 1 and bit 3, I apply X gates. This is the general representation. Right? So next I go to derivation is completed and primary encode. So yeah, we are discussing this point, right? Primary encode techniques, right? For example, here, this particular meaning is, that means what? First, this line, are you able to see my screen? So this particular line, the purpose is imports the quantum circuit class, that particular class, from the Qiskit package. Now this particular line purpose is, we just need in the class lets you create a qubits, apply gates, find. It is for classical data. And this particular QC, quantum circuit of 3, this particular purpose is whether you want to convert something or not. If you want to convert something, how many qubits we need? According to basis encoding, the number of classical bits is equal to the count of qubit size. So in this one creates a quantum circuit with the number of bits equal to the number of qubits. In our example, it is 3 qubits, all initialized automatically from 0, at 0, all zeros only. So here, the purpose of 3 is the count of, because your classical bit strings, you read as a 3 bits, and base encoding needs 1 qubit per 1 classical bit, respective classical bit. So for I bit enumerate, we are repeating the loop from 0, index per index 2, repeat the same thing. When it is matched with the 1, then checks whether the correct classical bit is 1 or not. If it is 1, apply X gate. If it is 0, by default it is 0, do not change anything. So in this way, we use here poly X gate. So we derived many things there, but here we just pass the value X of I, that's all. X of I, that's in Qiskit, X of I means it's a directly poly X gate. Right? For Y, X of Y, Y of I. For Z, Y of Z, like this way. Now, so this is something about primary encoding technique. For amplitude encoding, the main purpose, it represents classical data as amplitudes of quantum states. That means in previous in the encoding technique, we just combining, converting actual classical bits into equivalent qubit states. But there is no point of increasing of speed of processes because a classical bit only 0, but one quantum bit can show either 0 or 1. Multiple possibilities are there. So here we are taking that particular advantage. So for that purpose, we read, this is the basic formula. We read all the x vector x, it is state vector, we read all the values. The quantum state is represented with this formula. We directly implement the same formula to getting the amplitude encoding. So the main advantage of this particular amplitude encoding is exponential data compression or usage, because here compression means even though if you are passing n qubit values, 2 power and classical bit values, we can compress all those state vector into a particular n qubit values. Even though it's not the process, it's not the purpose, because how much work is possible to do by 2 power and classical bits, the same work we handle by n qubits. See here, 2 power n, n. So for example, if n equal to 1, I need only 1 qubit, but classical bits I need 2. If n equal to 2, I need 2 qubits, but 2 power n, 4 classical bits. Just imagine if n equal to 10, I need 10 qubits only, but I need 2 power 10 classical bits. 2 power 10 classical values should be necessary to compensate the work supported by 10 qubits. So if you have a well good support of the quantum hardware, these n qubits is enough, right? Because of the principles. So now, because it is efficiently for high dimensional data, as we discussed about, where we need to use quantum machine learning, when the dimensional data is more, and naturally it represents probability distribution directly by using the space and data values. And here, some possible challenges are we need a required a predefined state preparation circuit with a significant depth value. How much length we need for specific application, you need to predict how many maximum number of qubits we need. Sometimes your work capacity maybe need 10 qubits only, but you are supporting 20 qubits. Unnecessarily, we are wasting resources. So here, one more thing with respect to quantum state, every vector space should be in the position of normalization constraint, complicate implementation. That is the only thing. Anyways, if one hardware things are supporting easily, we can support this amplitude encoding. Now let's work on some hands-on example here. Amplitude encoding.
సో మీకు ఏంటంటే జ్ఞాపకం నాయుడు గారికి ఫోన్ చేయిస్తాను. ఫోన్ చేయించి నాయుడు గారి దగ్గర నుంచి సంతోష్ సార్ చెప్తే అంటే
So in case of amplitude encoding, we just use, first we need to read a state vector. I need an array of values of what type, whether it is complex or float. Once it is completed, you need to apply the normalization condition. Once normalization condition applied, you can go with the quantum circuit with that formula. So for that one, so for reading the array of values, I need NumPy, and from it is copy paste here. I don't want this time. Circuit in the same way. From this time, we need to pass compression formula that is existed in this one, quantum info, that is imported from same state vector. It is a relation between those two things. Now we take one variable. Here I extract from array of size. I can go with
అక్షయ అని ఒక అమ్మాయి ఉంటుంది.
4 classical bits. 1, 2, 3, 4. So according to our explanation, if you are giving 4 classical bits, how many quantum bits I need? How many quantum bits?
2.
2 only. Simple thing, right? So I am passing 4, 1, 2, 3, 4. Next, and this data type is I go with maybe float.
నేను పండ రమేష్ ఒకే దగ్గర ఉన్నాను. మీరు ఎక్కడ
Next is we need to implement that formula x by that np.
అదే అది ప్రాసెస్ డెక్వచ్చు కదా, అది లేదు రామన్ పెట్టింది ఆర్ఐఎం మామూలుగా
Of normalization. So I believe that you know about normalization. When we are squaring the amplitudes, that should be equal to 1. Normalization vector. Now I go with we pass that x value to here. Pass the x value here. And this password. Now my total number of qubits is equal to NP area of log 2 of that length x to make it now quantum circuit should be for this quantum circuit. I need to pass that entire n qubits. Fine. Now I need to measure, initialize that particular actual data in the range of my 10 qubits. So once it is completed, now I want to print what is my vector value, what is my probability value for that one. First I need I import quantum circuit state vector. I pass NP value 1, 2, 3, 4 values. Normalization vector next. Yeah. So here, what is the meaning of this line? What is this initialization and why they mention these 4 different probability values? For each classical bit, it's showing the probability of 0.18259, 0.36159, 0.55741, and 0.738. So here, that particular point is, we need to understand one point is when we're calculating so when we are calculating yeah, that state should be x naught of the state or x1 of the state or x2 of the state or x3 of the state. These four possibilities are there. So it requires 2 qubits to represent these 4 state values here 0, 0, 0, 1, 1, 0, 1, 1. Because we pass 4 values 1, 2, 3, 4. So to compress this 4 into 2, I need just only 2 bits value. If qubits are 2, total possibilities are 0, 0, 0, 1, 1, 0, 1, 1 only, right? Right? So the basic idea is each component maps to one basis amplitude. This is the central idea of amplitude encoding. That means you create a circuit with the appropriate number of qubits. By using the formula, you talked about that log m, log of length x, right? That determines the total mapping of how many classical bits are reading, and appropriately how many qubits we need to calculate. Those things we calculate here. And next one, so here almost we calculate something like for those 4 different values, it is like a normalization condition. Hope you remember the normalization condition, right? So if you read those 4 different states, then that should be action of any values of 1, 2, 3, 4, those any 2 values are 1 square, this value, 2 square, 6 square, post. Based on this calculation, you got what the value you are getting here? 0.18257 for first combination. That means I believe that, for example, 1 by 1 plus 4 plus 9 plus 16, 25 plus 530, 1 by root 3. So what is the value of 1 by root 3? Maybe this is something about you can calculate those things later. So based on those values, we initialized for 2 qubit states. Here I'm showing the 2 qubit state for 4 possible values. We are passing Q0 and Q1. We got with these 4 different amplitudes. For example, if you're passing 8 qubits by default, sometimes you'll get some doubt, right? For example, if I'm passing only 5 values, how many qubits you get? If you're passing 6 values only, there is a concept called padding. For the padding, by default, we start with the Ket0 notation, but we consider that as a 0 implementation part. So. Now, next point is amplitude increasing formula, right? So this is what we calculated for normalization purpose in Python programming. Now, angle encoding. So the main purpose of angle encoding is, in previous case, we calculated the probabilities and amplitudes. But here, in case of angle, for changing of phase or identifying multiple phases, we use this angular rotation encoding. The purpose is classical data to rotation angles of quantum gates. When I start explaining about, I'm talking about two different angles, theta and phi. So the main purpose is main properties are efficient circuit depth, and some of the properties it is supporting linear dimensionality. I don't remember exactly what the point is. So the basic formula is this one, common choice, theta equal to pi of x. And when we are applying for x gate, these are the possibilities are there. When we are applying x gate, it should be rotated to Ry. That means in Qiskit also you need to use Ry, rotation y gate. In previous I derived Rx formula, right? So let's see. So you do not remember about Ry matrix, Rx matrix, we can directly type Ry value only. We can get that particular value. Let's see this particular example also. We just go to Qiskit environment. Now I copy the same thing, import NumPy and Qiskit. Now, initially you can select any value for x because according to formulae, as I explained here, you need to pass the x value, right? That x value may be anything for an assumption. So x equal to maybe 0.7. That is a classical data value. Now you need to calculate theta value. That the theta value should be, what is the formula here? Pi of x. Then we can directly use pi value is already existed there, at x value. Now, once we calculated this one, for this one, we need to apply quantum circuit for this particular. We're passing x value on, right? We can go with only 1 qubit because we're changing rotation only, right? We don't need multiple. It's here. As here, I explained about the point, what gate I need to apply here, Ry gate. See, for this mathematical also, a lot of derivations are there, but for our time being, I'm showing this only Ry need to apply here. The equivalent representation of thing is here, Ry. For Ry, you need to pass theta value. On y-axis is there from, by default start from 0. Now print. You see it. So it is for this angle encoding, that is rotation is placed at this particular place, Ry 7 pi of theta. In that location, that is Ry based encoding, because the classical values, in our example, I take with x equal to 0.7, is converted into a rotation angle by using the formula theta equal to pi x and applied to a qubit using that Ry gate, rotation gate, that directly rotates the block space vector in the future value, that quantum future value. So here you know about already shown all the points also. Finally, that is the main point of angle encoding, that encodes the classical value as the angle of rotation. Previously amplitude, here angle of rotation on the block sphere. So when we want to fabricate the values, when we want to for your application, there is a necessity to change some angles. Better you opt which encoding technique? This rotation encoding techniques. So there is one more encoding technique is called, that is hybrid encoding. It's simple thing. We are combining everything, every combinations. So for example, take up all the things. Insulation. NP quantum circuit, quantum info. This time, I do one thing. For specifically combine everything, I need one library. Visualization. Then I need to apply for 3 different gates, 3 different bits. UC equal to quantum circuit of 3 qubits. I want to apply. So for rotation, simple thing direct. QC equal to RY gate for rotation purpose. That is what is the formula? Pi into x, right? Pi into, you can start with x equal to 0.7. Otherwise, I can directly pass the value also here 0.887. If the phase shift value is 0. This is about, this line is about this is first one. QC RY it is. When I mention RY, you need to understand that it is a by default what? It is an encoding. What type of encoding technique? Angle encoding. Next for QCX for quantum bit 1, I need to apply this one. For sample it here, it is a direct hardcode value. I'm not reading any values here. It is for encoding by direct basis encoding. That is 1 bit converted to 0 bit. Now amplitude, here I go with 1 vector. There is a big formula, NP dot array equal to this time I go with 2.0 or 0. This delta P simply combine multiple things. This is a flow type or complex type, both are acceptable only. Now I want to calculate normalization function. Using the same from linear algorithm, LIM, ALG, that is a predefined function is there for normalization purpose, normalization, but passing this vector value. In what I explained in the previous case, same thing. Now we take one variable. I want to initialize those things. What gate? Vector problem. Equal to. That label should be, you need to understand, right? Label value should be, for example, we start with the value. The tech notation. We can implement a bra notation also. Bra notations are nothing but row vectors. You see dot, append all the values for this init gate for rest of the 2 bits. And you see dot, same function. So here I'm not trying to explain the application point of view, but in what way you need to, all these things are basic for your quantum machine learning. The next I'll explain about the same point. So for this one, something is missing, which line from this quantum library? What is that? Because most of the functions are deprecated. Yeah, right. See here. Here I'm taking 3 qubits, and first qubit for rotation, angle encoding, second for direct basis encoding, third for combination. That is what we call amplitude encoding. So in this way, we can combine multiple things, and finally, as of now, what we did. This is the way we need to converting a classical, in regular machine learning algorithms, we use about classical bits or state vectors or the lists, everything. You will need to use these quantum gates, poly-X, poly-wave, poly-Z rotation gates. Then, once it is completed, here we come up with the quantum futures and kernels. The main difference between encoding and future map. So here, encoding means here, as of now, we completed encoding part only. It shows that how you put data into quantum state according to your requirement. But what is future map? How you build a QML ready embedding circuit for kernels and quantum support vector machines. So simple thing, encoding are basic building blocks. On top of the building blocks, future maps are structured templates built using those primitive encodings along with the entanglement. Here we are combining 2 properties. So there are multiple what we call for encoding. Here we have a classical burst in the qubits, there are the other we explain the same thing, basis, angle, amplitude, and everything. For future maps or built-in QML embedding by default templates, we have these maps: Z map, ZZ map, IQB map. Here I mentioned the basic things. The basic purpose of Z future is encoding classical futures through Z rotation gates applied sequentially. Classical futures. In case of ZZ future, adds entanglement. See, in case of Z future, we just converting classical futures into some on top of the quantum representation, hyperplane representation. In case of ZZ, along with that one, I'm adding entanglement also. Hope you understand what is entanglement. If one particular thing changes, automatically it reflects the other thing also. You can implement the same thing by using the Hadamard gate. So for Hadamard gate, I can go with one Qiskit composer. So are you familiar with the Qiskit composer? Qiskit composer.
మరి
The
మీరు
sessions are
లాగిన్
feeling boring.
ఓకే 4 వరకు మాకు 4 అవ్వచ్చు మేడం.
Right.
ఓకే ఓకే మరి చేయండి అయితే మీరు లాగిన్లో ఉండండి, దాన్ని బట్టి మీరే ఇది అవ్వండి. నెక్స్ట్ ఈ స్పీకర్ రేపు కూడా కంటిన్యూ చేస్తారు, ఓకేనా? మీ లాస్ట్లో చిన్న విషయం అదే
See, as of now, we talking about all the theory part, right? See here, all these things are here. So by default, your quantum value starts from, as I explained in the encoding, by default it's from 0. For example, if I'm passing a Hadamard gate here,
ఓకే
by default it is called superposition gate.
బాయ్.
If you look into unit space or Q space here, it representing two possibilities. If I'm dragging one more Hadamard gate, it can get 4 equal probabilities because it's already know the possibility. It's already having all the 4 answers. And if you're passing one more Hadamard gate, it's giving me 8 different possibilities. See here in block pair. So for showing, it is showing the angles, but how it is calculated, it depends upon the X, Y, Z gate, rotation X, rotation Y, rotation Z, RX, RY, RZ. After that, based on that one, we go with the data encoding techniques. Again, after data encoding, we go with the what we discussed now, kernels, future maps and kernels. So now, it is the basic circuit structure for Z future map. Here, see here, we're combining RZ with the poly X, poly X, poly X. So for this one, also we have a specific demonstration point of things are here. So main purpose is when you want to phase rotation, jet future map is the best part, phase rotation. Here we are not changing any amplitudes, only phase changes if required. Here we are this jet map, future map doesn't support any non-linear dimension interactions or no amplitude changes, only for phase shifts. For phase shift we use RZ gate. So for that one, I need the same thing available in from circuit library itself. We have a direct function. That future map is a direct function. Now, these number of features you can define. For now, my number of features may be 3. For any particular application, number of features may be 3. In that case, I want to apply the same jet future for those 3 values. Num underscore feature variable. Then I want to print Z map of. There we use quantum circuit. Here we are using Z map. So here it can generate 3 angle faces here. See here, 3 different angles. Hope you remember this one. What is H? What is H here? See, you already shown here, right? Here in the where is that composer, quantum composer? This one, Hadamard gate. All these possibilities here. It is 12.5%, 12.5, 12.5, 12.5, 12.5, 12.5. Here I'm not passing an application, by default showing the 12.5% possibilities. But here in Qiskit, when I pass in three values, it is giving the same properties. X of 0, 0, X of 1, 1, X of 2, 2. Depend upon the requirement, even it can follow the complex values also. So for phase shift only, we use this Z future. In case of ZZ future, the second one, it is for entangling ZZ gates. For entangling, we need this exponential value of things value, Xi, XZ value. These two interacting terms are important. And this is for the default gate of circuit structure. Here we use angle encoding and 2-qubit entanglement also. This is for non-linear representations. We can try some sample code for that also. You can take the same story, but here just replace with this Z feature map and same ZZ and for clear difference Z, and the volume function is also Z feature map. Number of features along with how many repetitions you need, how many entanglements you need. You need to present choice. See here. It can use, if you look into these two, it go with the angle shifting and also possible with the two states, two entanglements, two different states with the X gate. And the next point is IQP. This is at dynamic time or peak time instantaneous quantum polynomial. Here, it is something like, here I mentioned the by default gates also. In what way in digital logical design you'll enable full ladder, half adder, same concept here. If you go in depth, you will get more math in that one. But you are lucky enough for application purpose, we have a Python libraries. We can work with, even though if you are not familiar what is happening inside, fine, it's okay. So it is here in this one. In first case, there is no entanglement, only phase shift. In ZZ way, we are adding entangle for 2 qubits. Here in the IQP instantaneous, we are combining three things. One is the superposition and angle encoding and deep entanglement also. More than we are combining ZZ and Z gate also. For that one, okay. Now, as of now, we learn about data encoding techniques, and at the same time, we learn about quantum kernels and futures. Now we combine all the things and we try to perform on a particular, what can I say that, quantum support vector machines. Let's go to that topic. For instance, we just start with the basic thing. So the main specific difference between here, I'm showing this the same difference here in what things they are using, in what way they are using all these quantum gates along with rotation matrices, data encoding techniques. This is the basic representation. When we are passing a data set, in what way it is estimating the quantum kernel. It contains noise simulation, noiseless simulation, and trapped ion quantum processor. Here inside that one, as of now, we talk about this Hadamard gate, RZ gate, RY gate, all these rotations only, this circuit structure. So the main purpose is here, in case here, when the classification data is more or high dimensional data, quantum support vector mesh is suitable thing because within polynomial time, it will give high accuracy. Here, we implemented the same thing on BRISC database. It's showing that somewhat better than the regular support vector machines only. Let's see that particular example here. So here the assumption is, in this particular final program, we try to compare